As you start into section 7.2 notes, we are going to address 3 of the objectives that you can find in the front of your note packet. It's objectives 7, 8, and 9. And this is some nice review from Algebra 2X. Objective 7 is use the difference theorem and determine if a model is polynomial and to what degree. 8, we're going to find a polynomial model algebraically. And number 9, find a polynomial model with a calculator via a regression. So let's just dive right into the notes. The first thing we want to talk about are called Figureit numbers, and I just want to show you what these 3 types of numbers are here, so then we can get into looking at polynomial patterns. Figureit numbers are a number of points in a pattern sequence of familiar geometric shapes. So if we look here, we see some figurative numbers. They make a pattern in geometric shapes, and we'll deduce what that pattern is in a little bit. Triangular numbers are a number of points in the nth triangular array of dots. So they want us to find T of 6 right here, and these are the triangular numbers, the 2-dimensional ones. And we can see here that we have pattern number 1, 2, 3, 4, 5. This next one would be T of 6. And if you look at the pattern, you should be able to deduce that they're going to do is they're going to take the existing 15 dots and add another row. The row they're going to add to it is going to be a row of 6. So 15 plus 6 will tell us that T of 6 will equal 21. So the 6th triangular pattern will have 21 dots in total. The third type of number is a tetrahedral number, and it's the total number of points in a 3D tetrahedral array. So triangular numbers are 2-dimensional. Tetrahedral is kind of stacking triangular numbers. And here you're going to see stages 1, 2, 3, and 4. They want us to find here what is the value of T of 5. If you take a look at this and look for a pattern for laying things down, they're going to have to come on in and actually add another triangular kind of pattern below to stack it. T of 4 currently has in it 20 dots as a total. When they add one more layer of dots on the bottom here, they're going to end up adding 15 more dots. So it'd be 20, the existing 20 dots plus another layer of 15 dots. So therefore T of 5 will equal 35. Now the book wanted you to see some number patterns in that previous slide, more of a geometric form. We're going to look at number patterns as an Algebra 2 form. And this is really a big part of today's lesson, is looking at patterns of constant differences. In our first table of data here, this is data or ordered pairs for this particular linear equation. And what we notice is when x is 0, you put it in, you get 2. When x is 1, you get 7. X is 2, you get 16, and so forth. And what you're going to want to do today is find out or prove that this is a linear function. And here's what you do. You take the output, or the y values, which is right here, and you find their differences. So you say, what is the difference between 2 and 9? Well, it went up by 7. Okay. What's the difference between 9 and 16? That also went up by 7. 16 and 23 went up by 7. And what you're going to see here is every piece of the output, or the y values, are going to have an increase of 7. And what this tells you is that it just took us one try to get a set of constant differences. Now, let's take a look at the next example and find its constant differences. Now, if you take a look at this, this is a quadratic function. We can see that. Now, if we take the output, or the y values, which is right here, the constant difference between 4 and 4, there's no change. Between 4 and 6, it goes up 2. Between 6 and 10, it goes up 4. 10 and 16, up 6. And then you're going to see this pattern here. Now, what we're trying to do is find constant differences, so what we need to do is go to the next level. Look at the differences of the differences. From 0 to 2, we had to actually increase by 2. From 2 to 4, we increased by 2, 4 to 6, and so forth. So hopefully you can see a pattern here. And this is actually a theorem that you can use. It's the constant differences. When you have a set of ordered pairs or input and output related to a particular equation or function, if you take the output or the y values and try to find when the differences are constant, whatever level you get down to will be telling you what is the degree of the function. This one right here, this is the first set of differences we did. First set means it's degree 1. Okay. Here, the first level did not work. We had to go to level 2, which means the second set of differences worked. Therefore, it is degree 2. And a degree 2 means it's a quadratic function. And that's how this theorem works. Now, if we formally talk about the differences theorem, it says this. The function with the equation y equals f of x is a polynomial function of degree n if and only if, for any set of x values, there are consecutive terms of an arithmetic sequence, the nth differences of the corresponding y values are equal and non-zero. Folks, what that told you is this. Go back to the last slide. Look at the outputs or the y's. When you find your level of differences, however many levels you went down is the degree of the function. Now, arithmetic sequence, by the way, is a series of numbers that have a constant difference. That's all that is. So look at this kind of quiz number 3 here. It says the fifth differences of this particular function, whatever that is, are all equal to 3. What is the degree of the function? What they're telling you is they had to go and find the differences 5 times until they equaled. Therefore, this function is considered to be of degree 5. So a polynomial of the 5th degree. Now, if we go back to the data from that first slide, which was called the tetrahedral numbers, they want us to do this. Construct a table of consecutive tetrahedral numbers and take the differences between the consecutive terms. They want us to figure out what degree it is. So let me just show you. This was these were the tetrahedral numbers here. We had that when x was 1, we had 1 number. When x was 2, we had 4. When x is 3, we had 10. When x is 4, we actually had 20. We did determine down here when x was 5, we ended up having 35. And I'll tell you when x is 6, you're going to have 56. Okay. They want us to figure out if we were to put this data and graph it, is it a linear function, a quadratic, a cubic, a quartic, and what have you. So just look at the differences, as simple as that. So right here we have the differences is going to be plus 3, 6, 10, 15, and 21. Clearly we have to go down to the next level. Difference between 3 and 6 is a positive 3. 6 and 10 is 4. 5, 6. We're going to have to go one more level. The differences here is plus 1, plus 1, plus 1. Because I had to go beyond 1 level, 2 levels, into 3 levels, this function is a degree 3 function. Okay. Now let's look at the next slide because they want us to. We're going to take this data and actually put it into the graphing calculator and do a regression on it. Now, what you want to do first is do this differences theorem to figure out what regression to do. If we know this is a degree 3 function, we're going to go ahead and do a cubic regression. So let's take a look at the next slide for the calculator portion. Okay, so going to this slide next, here's the scenario. It says use a regression to determine the polynomial for the cubic. Now, you had the data, so what you're going to want to do is go into your calculator, and you're going to want to do go into Stat, Edit, and go in and enter in List 1 and in List 2. In List 1, let's put all the x values. In List 2, let's put the y values. So, for example, our x's for the tetrahedral numbers, we had 1, 2, 3, 4, 5. The corresponding y's were 1, 4, 10, 20, 35. And you could also add at the order pair 656. Okay, once you have that, now go back, remember, and do Stat Calc. And what you're going to want to do is scroll down and look for the cubic regression. Okay. Once you do the cubic regression, you will end up getting information that will look something like this. It'll come out on the screen. It'll say cubic regress, and it'll be in this polynomial format here. And just as we did in chapters 2 and 3 when we did regressions, they're just going to give you the output. They're going to say what A is, what B, C, D, and so forth. What you should get for the final equation for this one, it's going to look like this. Y will be equal to 0.167x cubed plus 0.5x squared plus 0.33x. And what we just did is we found ourselves a polynomial regression. Okay. Now just go back a slide in your notepad, because this one here, solving a system to find the polynomial model. We're going to again just keep looking at those tetrahedral numbers. And what you can do here is I'm going to show you how you can set this up by hand. I'm not going to walk you through it, but I will show you the process for it. Now this here was the data that we had, and what you would do is this. If you wanted to come up with a model, think of it this way. This here is considered to be the input, right, and this is latter half obviously is the output. So the output for this is the answer. The output goes right there, and then the input is what in this case, what n would be. So, if we used x and y, typically, these would be the x's here, it'd be x cubed, x squared, and so forth. And then this right here would be the y. So if you think about putting it in here, here's what you do. You take the first ordered pair, which is 1, 1. So y is 1, so I'm going to start in the equation and put t of n is 1. The answer to this is 1. Then I'm going to go where the n's were, and I put in 1n for the x. And then I'm going to do b, 1 cubed, plus c times 1 plus d. And then you do this again. You're going to do it for the next ordered pair. In the second ordered pair, the answer is 4 this time. So 4 when the input is 2. So you put 2 in for n, or in this case the x. So you'd have a 2 squared plus b, I'm sorry, this would be a2 cubed actually, b 2 squared plus c times 2 plus d. And then the next one is the order pair 3, 10, so the answer is 10. And you're going to do a, and we're putting in 3, and we cube that, putting in b, 3 squared plus c 3 plus d. And then you wrap it up with the fourth ordered pair. When the answer is 20, you would do a 4 cubed plus b 4 squared plus c to the fourth plus d. Now what you have to do is we here wrote ourselves a system of equations. If you take a look at it, I know the input and the output. I need to figure out what a, b, c, and d both are. And in this case, that's 4 unknowns. When you have 4 unknowns, you need 4 equations. So what you would do is you could find a polynomial equation by hand. Now I'm going to tell you I'm not going to require you to do this, but I am going to tell you this. Go to the book. They actually show you how to write this polynomial equation by hand. You definitely will be required to do it with the regression analysis, and the regression is very straightforward. Just put the data into your calculator and do stat calc. In this case, it was a cubic regression. But I do encourage you, there may be some possibility for extra credit in this chapter, and if so, this tends to be a type of problem I would ask you, is to find the regression by hand. So just take a look in your notes. Now the last slide we're going to do is this one here, and if you want some extra practice on figuring out how would you find the polynomial formula for this, I'm going to challenge you to pause the slide, do the constant differences and figure out what degree this data is, and then what you would do is do a calc regression on that. So pause the video, come back here, and I'll have the answer up to see what degree this function is so we know what regression we would do. Okay, and if you did it, what you're going to find is you take the actual data, the x's and the y's, or the input and the output, and look at the differences of the output or the y's, and you have to go down to the third level to get constant differences. Therefore, this would be a cubic regression you would do. And again, put this in list 1 in your calculator, this in list 2, do a stat calc cubic regression, and you will get the right formula. Let's take a look at the assignment for this section. I'm not going to cut anything from this assignment, but I will suggest to you to use the differences theorem on numbers 4 through 7 when it asks you, show how you use the differences theorem. If I choose any of numbers 4 through 7 as a homework quiz, I expect to see some work on how you figured out the degree of the polynomials. So again, show the use of the sum of differences for 4 through 7 within the assignment. And that's about it.